Welcome students to this short recording on multiple linear regression. As we are approaching the end, I'm sure we are left only with multiple linear regression and multivariate techniques. So in this recording, I'm going to take you through multiple linear regression. I think the word multiple says it all. Here now we are dealing with a number of independent variables, unlike in the simple linear regression case where we were connecting just a dependent variable, a single dependent variable on a single independent variable. In multiple linear regression, we are connecting a single dependent variable on a number of independent variables. Now, we are saying multiple linear regression, we are using more than one predictor. You see, the independent variables are sometimes called explanatory variables or predictors because they are used to predict the dependent. In some other fields, such as economics, they are referred to as exogenous variables, and the dependent variable is referred to as an endogenous variable. So if we include more than one predictor, so the predictor we are referring to the x values or the independent in the model, we call that multiple linear regression. So if we include more than one, but if we have one, we call that simple linear regression. Predictor variable, the xi's, are usually called explanatory variables. I've already said this, which are used to explain why. In other words, the explanatory imply that we use them to explain the behavior of y. Variable y is called the response or endogenous or simply dependent variable. All those names, they refer to the same variable y. Linear model of multiple explanatory variables, still single response variable, multiple linear regression. We also have, you see, sometimes we talk of polynomial regression. I'm going to demonstrate some nonlinear forms of multiple regression, the polynomial, the quadratic forms, and so forth. But in this particular video, I'm only going to focus on the linear part. Now, simple linear regression considered only the relationship between one dependent variable and one independent variable. Now, the possible effects of other independent variables is ignored. You see, that makes simple linear regression a bit non-practical, though it's used in practice. But when you look at the real situations, it's very rare to always find a dependent variable which is being influenced by only one explanatory variable. Now, for example, we may describe how the repair cost of a car is related to the age of the car. I'm sure as the car becomes older and older, we expect the repair cost to be high because you have to replace a lot of other things. Now, but the question is, are there other factors that affect the repair cost? Does the size of the engine or the number of kilometers driven affect the repair cost? When several independent variables are used to estimate the value of the dependent variable, it is called multiple regression. I think I've already said this. You can think of so many other problems which can be a candidate to multiple linear regression. If you look at yield, for example, what factors affect yield? Is it only the type of variety used? What of rainfall? What about the amount of rainfall? What about the land size? What about the amount of pesticide applied? What about the soil type? So if we bring all those possible factors and we try to model how they affect a dependent variable, then we are talking in the context of multiple linear regression. So I have a couple of examples here. Weight gain of animals depend on age, feed type given, breed, and so on, that could be a candidate for multiple linear regression. Crop yield depends on fertility status of soil. I've already given you this example. Variety grown, amount of rainfall received, spacing, humidity, temperature, and so forth. You see, all those factors will affect crop yield. So a multiple linear regression model is of the form yi equal to beta naught plus beta 1x and so on up to beta nxn plus ei. So this is the linear form of this is the multiple linear regression model. Xi is the ith independent variable. Beta naught is the value of y when all the independent variables are 0. Usually this beta naught, you see when you put x1, x2, x3 up to xn equal to 0, we get y equal to beta naught. So beta naught is sometimes referred to as the intercept, or the value of y when we set all the other, assuming that the independent variables have no impact. That is when we set them to 0. What is the original value of, if we say, okay, fertility status of soil is 0, it's not having an effect on crop yield, variety grown is not affecting, rainfall is not affecting, then the beta naught will be the yield, assuming all those independent variables are set to 0. Beta j is the net change in y for every unit change of xj, holding other independent variables constant. That is very, very important. So this beta j, we are actually saying that is the regression coefficient corresponding to xj, to the independent variable xj. So the regression coefficient is beta j. Now, if we set all the other independent variables to 0, what will be beta j? Beta j is actually a change in y for a unit change in xj. That is important. So ei is the residual or error term. Now, just like the analysis of variance model that we looked at previously, a multiple linear regression model has got a couple of assumptions, and I have 5 of them here that must be met. So whenever you are doing your research and you have decided to use a multiple linear regression, you must make sure that these assumptions are not violated, because the validity of the multiple linear regression model depends or is dependent upon the assumptions being satisfied. In other words, they must not be violated. If those assumptions are violated, your model suffers drastically in terms of predictive power. Remember, when we do multiple linear regression model, we want to be able to forecast. We want to be able to perform what we call what-if analysis. So we don't just fit a model for the sake of it. When we fit a multiple linear regression model, it must help us to tell the future, to extrapolate, to interpolate, to perform what-if analysis. So all the ability to do all those things depends on the assumptions being satisfied. Now, one assumption is that we assume that there is a linear relationship between the dependent variable and each of the independent variable. That is very, very important. Linearity assumption. We can't talk of multiple linear regression if there is no linear relationship between the dependent variable and the independent variable. So that is a very, very important assumption. You need to test that assumption before you fit in a multiple linear regression model. But non-statisticians, they don't see it necessary. What they do, whenever they get data, they go on the computer, they click, analyze multiple linear regression, they put their dependent variable on the dependent tag, independent variables, and then they run. They don't ask themselves, is it logical to assume linearity? Is there a linear relationship at all? So how do you test that? You need, before you fit in a multiple linear regression, you need to construct scatter diagrams. Each independent variable versus dependent. So if you have got, say for instance, 6 independent variables, you need to produce 6 scatter plots to check if it is reasonable to assume linearity between your dependent variable and each of the independent variable. If you see a cup-shaped curve, then you still go on to fit a multiple linear regression. Surely something should be wrong, because the assumption of linearity will be seriously violated. Now, assumption number 2, this one is called homoscedasticity assumption. We assume that the variation in the residual is the same for all fitted values of y. All fitted values of y, we assume that the variation in the residuals is the same. Otherwise, if not, we say there is heteroscedasticity. If there is heteroscedasticity, actually we call that a monster when it comes to multiple linear regression. It is a monster because it affects the predictive power of your multiple linear regression model. So we have to ensure that there is homoscedasticity. Now moving on to number 3, we assume that the residuals are normally distributed with a mean of 0. This is very, very important. In fact, for completeness, the residuals must be independent, normally distributed with a mean of 0. Now, we also assume the absence of multicollinearity. What is multicollinearity? Multicollinearity exists if the independent variables are correlated. I'm sure we understand when we talk of correlation, the strength of the relationship between 2 variables. So if we are fitting a multiple linear regression y equal to beta naught x plus beta 1 x1 plus beta 2 x2, the x values, that is x1, x2, x3 up to xn, each of them, pairs of them, must not be correlated. If we calculate the Pearson's product moment correlation coefficient, we must not conclude that the coefficient is significantly different from 0. In other words, we don't want the independent variables to be correlated. If they are correlated, we have multicollinearity. And multicollinearity is a problem when it comes to multiple linear regression. So the assumption is that whenever we fit a multiple linear regression, there is no multicollinearity between any pairs of independent variables. Now, we assume that successive residuals should be independent. I think I've already said this. The residuals must be independent. They must be normally distributed with a mean of 0. That is absence of serial autocorrelation. So autocorrelation is when the residuals are dependent. The residuals must not be dependent. If they are dependent, we say there is serial autocorrelation or first order serial autocorrelation. Independent variables must not be correlated. If they are, we talk of multicollinearity. So these are the 5 assumptions of the multiple linear regression model. Dear students, whenever now we are fitting a multiple linear regression, I will repeat this. Ensure that the assumption 1 up to 5 are satisfied. I have an example here where I have given data for sales of farm produce in thousands of dollars. So the sales is our y variable, and we assume that these sales are being affected by 3 independent variables. So this is our x1, this is our x2, and our x3. So we'll have beta naught, beta 1, beta 2, beta 3. So we want to fit multiple linear regression to this data. This is the output from that data. Please, you can run the data to see if you are able to produce the same output. You can do it in SPSS, you can do it in whatever package that is available for you. You can do it in ARA, you can do it in SAS. I've done it in MINITAB myself. So what we have is the MINITAB output. My main interest is for you to be able to appreciate the meaning of an analysis of variance. What is it that we want to achieve by producing an ANOVA table for in a multiple linear regression case? So the ANOVA table is basically used to test, we call it a global test. The global test is that there is no linear relationship. No linear relationship exists between the dependent variable and the set of independent variables, versus there is a linear relationship. That is the assumption that we are, that is the ANOVA, that is the hypothesis, sorry, that is the hypothesis that we are testing. There is no linear relationship, that is our H naught, between the dependent and the set of independent variables, versus H1, which says there is a linear relationship. So we look at our p-value here. You can see that that value is less than 0.05, it is less than 10%, it is less than 1%, any acceptable alpha level to which the test is being done. So you can conclude that no, there is a linear relationship, because we are going to reject H naught. Remember, that's how we have been rejecting H naught in our case. Or alternatively, you can compare the F cal, which is this value, with the F critical. In this case now, our F critical will be F, if you are doing the test at 0.05, we'll have our 0.05 here, F at 0.05. What is the numerator? Maybe numerator will be, numerator will be 3, the degrees of freedom for that one, and the denominator will be 11. So look at this value from the tables. I'm sure you know how to look. And then we reject H naught if this value here is greater than this. And I'm sure this value will be lesser than this one. So in which case then it means still we are saying a linear model is appropriate for the data that we have. That is for this data. This data can be modeled by a multiple linear regression model. Now, is that enough? Surely, when we have this, it means we then go on to look at each individual variable in our model. Advertising, promotion, and competitor, sales of competitors. So sales of competitors, it's a significant variable in the model. Promotion is also significant in the model. Advertising significant in the model. All of these are significant at 5%. But if we say at 1%, then we will only remain with advertising. So in actual fact, the model will be reduced to a simple linear regression, in which case we need to remove this one, because we are saying it's not a significant variable in the model. So I want you to take note that this p-value here, we just use it to screen if we are supposed to retain all the parameters in the model, or some of the parameters are not necessary in the model. Now, the model summary that we have here is used to check if our model is the strength of the model. Remember, the R square adjusted. Of course, I'm going to give more details at the end, but you check, the higher the value of R square adjusted, the better the model, the multiple linear regression model. Otherwise, we normally prefer R square to be very high, 90 and above and so forth, for the model to be quite good. Because the R square is just the percentage variability in Y, which is being accounted for by the independent variables. Now I want you dear students, to look at this table here. This is an important table. This is a t-test table. Firstly, this table helps us to write now the model, the actual multiple linear regression model. These are the coefficients. So we'll say cells is partly constant. You can see that is our beta naught plus beta 1 x1. So beta 1 is 49.0 advertising plus 59.7 promotion minus, I want you to take note here, 1.838 competitor cells. That is the multiple linear regression model that we fitted. But more importantly is again to look at the p-values. These p-values are based on a student's t-test. We did this when we were doing biostatistics. So we are testing the significance of each of these models, of each of these variables in our model. In particular, we are testing the model H naught, H naught beta I equal to 0 versus H1, which says beta I is not equal to 0. This is the model that we are, this is the hypothesis that we are testing here. So what I want you to take note of is that when we fail to reject H naught, we are saying the coefficient is not significantly different from 0. If we say the coefficient is not different from 0, we are actually saying it is equal to 0. So if it is equal to 0, it will multiply the x1. For example, if we say this one, if we say beta 1, if we say beta 1 is equal to 0 in this model, it means we will say 0 times advertising expenditure. So advertising expenditure will become 0. So we will only remain with the cells y equal to 65.7 plus 59.7 promotion minus 1.838 competitor cells. But if we fail to reject H naught based on these p values, it means that we will retain that particular independent variable in our model. That is very, very important. So we use the coefficients, table of coefficients, to decide on whether we need to retain a variable or we need to do away with the variable. Now, I have an important column here, which is called the variance inflation factor. What is a variance inflation factor? Let us see that as we proceed. But before we look at that, I want us to look at the residual plots for cells. These plots are important as they are used to check whether the assumptions are violated or not. This one is called the normal probability plot. You see, we want these points here, these points, to lie very close to a linear line. We don't want these points to be scattered far away from the line. If they are scattered, it means a violation of the normality assumption. Remember, we said that the residuals, they are normally distributed. So we use this plot here and also this plot to check for normality. I will not want to repeat what we did in biostatistics. I want you to go back and reflect on that, because this is the plot of histogram. When do we say normality assumption is not violated? Remember the issue of symmetry around 0. You know, when you look at the shape, of course not the theoretical normal distribution shape, but when you look at the histogram, how does it look like? Does it show any sign of skewness? This is just visual inspection. So these two, you can see we want the points to lie on a straight line. We want to see a clearly curve-shaped curve. Now, this one, residuals versus fits, is used to check the homoscedasticity assumption. We want these points not to exhibit any pattern In other words, they must be, when you draw a line around them or a shape around them, the shape must be rectangular. We don't want a situation whereby when you draw, maybe you end up having a shape that shows an upward trend, so that you can say as the values becomes higher, the residuals also becomes higher. We want a situation whereby you see here, I can see that the assumption is not violated. You can see when you draw a line, a shape enclosing all of this, that shape must be more like rectangular. But if you have some points that are almost lying upward, so that when you draw a shape, you don't get a rectangular shape, it means a violation of the homoscedasticity assumption. And in actual fact, you will say we have heteroscedasticity. So you need to try and make sure that that is corrected. Now, when you look at the plot of residuals versus the versus order, we use this to test for the independence of error terms. Remember, one of the assumptions, we say the error terms must be independent. So the only assumption which is not being tested by the residual plots for cells here is the assumption of linearity, which I said you can make use of the scatter diagrams to test for linearity. So normality is being tested, homoscedasticity is being tested, independence of error terms is also being tested. Again, we don't want to see a pattern here, but I want to encourage you to check, how do we interpret this plot? What can we say when you look by merely looking at this plot? And dear students, I want to encourage you, we don't have to give you everything as teachers. As teachers, we must also teach you to be independent. In other words, the teacher can supply 40% of the work, of the content, and you have to look for the remaining 60%. So what I'm saying, I want you to do yourself a favor, go to residual plots, interpretation of residual plots in multiple linear regression. Just look for books or material to check, how do you interpret this? How do you interpret residual versus order? When do we say there is a serial autocorrelation? You see, we say if the residuals are dependent, we say there is first order serial autocorrelation. So here we are testing for that using residual versus order. Then residuals versus fits for homoscedasticity, frequency versus this, residual versus frequency for normality, and so forth. But more importantly, there are other formal tests that can be conducted. When I'm saying formal test, it means the formal test of hypothesis. So for normality, there are so many normality tests that we can talk of. I want you to think about them, which normality test can be performed. For example, even the chi-squared goodness of fit can also be used to test for normality. Kolmogorov-Siminovi can also be used. Anderson-Darling can also be used. So all those Lilliefors test, for example, it's still for normality. But the one for autocorrelation, I only know of one. That is the Deben-Watson. We call it DW test. That is the Deben-Watson test. It's a formal test. Now the residuals versus fit, I know there are now three. We have what we call the Bartlett test. And we used to have the Levin's test, but I've seen now there is a modified Levin's test. All the three tests, they are used to test for constant variance. So Levin, modified Levin, and Bartlett. Deben-Watson, the normality test, there are many. So think about them and make sure you know. Now, what is the use of ANOVA? I have already explained this. I said this is a global test. So the ANOVA is simply testing that all the regression coefficients are zero, in which case then it means there is no relationship. versus no, there is at least one which is not 0. This is what you can also write it this way. Here I've written it in mathematics form or statistical form. H naught, there is no linear relationship between y and the x's. There is a linear relationship. So we reject H naught if p value is less than alpha. If H naught is not rejected, we do not proceed to interpret the rest of the output, because we are saying this relationship does not exist. So what other interpretation would you have to do? So, but if we reject H naught, then we proceed to interpret the rest of the output. Now, so I have brought again the same output, testing individual regression coefficients. Ladies and gentlemen, I think I've explained this. So we basically use this one. But now I brought this back because I wanted to explain the variance inflation factor that I talked about. The variance inflation factor is a measure of the degree to which an independent variable is correlated with the other independent variables in the regression model. So we don't want these to be correlated. Remember, we said when they are correlated, we talk of multicollinearity. We want them to be uncorrelated. So what MINITAB has done, it fits the variance inflation factor for each of the variables. So this is very, very critical to screen that independent variable which is not needed in the model, the variable which causes multicollinearity. So now, that is the variance inflation factor. The variance inflation is computed for each independent variable xj by first regressing xj on all the other independent variables in the model to obtain r squared. The variance inflation factor for each independent variable xj is then calculated using VIF equal to 1 over 1 minus r squared j. So this is the same formula which is being used to calculate this. You can verify that. You can try to check if you use the other formula to get this. If you use this formula, are you able to get those variance inflation factors which are given? So how do we interpret this? This is very, very important. We are saying a VIF greater than 10 is unsatisfactory and indicates that the independent variable should be removed from the model. A VIF of 10 or greater is equivalent to an r squared j of 90 or higher. So what is the interpretation? VIF ranges from 1 upwards. The numerical value for a VIF tells you in decimal form what percentage the variance, the standard error squared, is inflated for each coefficient. For example, a VIF of 1.9 tells you that the variance of a particular coefficient is 90% greater than what you would expect if there was no multicollinearity, if there was no correlation with other predictors. So I want to give you a rule of thumb on how to interpret the VIF. So 1, not correlated. So if we have 1, we are happy. Greater than 5, highly correlated. Exactly how large a VIF has to be before it causes issues in a subject of debate. What is known is that the more your VIF increases, the less reliable your regression results are going to be. In general, a VIF above 10 indicates high correlation and is cause for concern. Some authors actually suggest that if a VIF goes above 2.5, it is actually not good. Sometimes a high VIF is no cause for concern at all. For example, you can get a high VIF by including products or powers from other variables in your regression like x and x squared. If you have a high VIFs for dummy variables representing nominal variables with 3 or more categories, those are usually not a problem. So I want you to take note of the interpretation. Watch this video in conjunction with the notes. I'm going to give you the second segment, which is the final segment on multiple linear regression. I will post this on YouTube. Please, in case you want to get any clarity, you can also check on my YouTube channel. Post your comments on our various platforms so that we are able to respond to you. In case you don't understand a particular concept, feel free to post either on YouTube or on our Moodle platforms. Then our well-able teachers will respond to to the questions. There is the coefficient of multiple determination. I think I explained that. I will bring this back. That is the proportion of variation in the dependent variable y, that is explained by the set of independent variables xi. So we want that proportion to be high. Otherwise, if the r squared is low, it means the model has excluded key variables or variables which are more important in the model. So we want all the important variables to be included in the model for it to be a good model. So as the number of independent variables in the regression model increases, the coefficient of multiple determination r increases as well. Even if the additional independent variable is not a good predictor, its inclusion in the model increases SSE, which in turn increases SSR and R squared. Because of this, another measure of effectiveness of multiple linear regression is called R square adjusted. So instead of using R squared is not good enough, because you can get an R squared not because the model is good, because you have a lot of independent variables that you have included in the model. I want you to take note, in multiple linear regression, there is a concept of simplicity and parsimony. You see, we want a parsimonious model. In other words, the model must be very simple, but it must have higher predictive power. So to make it simple, a model must not be congested with so many independent variables. We must have fewer independent variables, but it must capture greatest percentage in the variability of y, which is accounted by those fewer independent variables that have been included in the model. So what I'm simply saying is that R squared does not take into consideration the number of variables in the model, but there is R square adjusted. This one is adjusted for the number of parameters or independent variables that have been included in the model. So in most cases, we want to rely on R square adjusted instead of just R square. So I have rewritten back the regression equation which we have fitted, and I want you to be able to interpret. But the interpretation is that when we set all the parameters to 0, the sales is $65.7 thousand. But for every unit change in the advertising, there is a 49.0 increase in the sales. You see, holding all the other variables constant. I'm so happy with the way this data is behaving when I look at the practical part of it. Look at the competitors. We are saying for every unit increase in the sales of competitors, there is a 1.838 decrease in the sales. This is quite good. Pick n Pay and ShopRite, they are competitors. If sales for Pick n Pay increases, surely the increase in Pick n Pay sales might be at the expense of ShopRite. So we expect basically that more customers are now going for Pick n Pay and avoiding ShopRite. So ShopRite might experience a decrease in sales. That is what the model is saying. So whenever you fit a model, you must also try and check if the model makes practical sense, because the model is at an abstraction level. At the level of modeling, we are saying it's at an abstract level. But what we want to explain is reality. We want to come down to the practical level and try to put a big elephant in a room and investigate it and try to get its behavior and so forth. That is basically what we mean when we are looking at a model. So this is the end. Ladies and gentlemen, we wait for the next short segment on multiple linear regression, where I'm going to talk of the variable, the variable selection procedure and so forth. Thank you very much. Enjoy.